So we just learned about diffraction and how it really is fundamental to the idea of having some sort of resolution, right? Some limiting ability to see small things. For the next several lectures, we're going to work in what's called the ray optics geometric limit, and we're going to look at the ray optic limit where we completely ignore diffraction. Okay? So we're going to do that just by assuming that the openings are all large compared to the wavelength of light. We're just going to take it to the complete limit, and we're just going to say, I'm not even going to worry about diffraction at all. And we're going to treat everything as a ray. So we're going to take our electromagnetic field, and we're pretty much going to ignore the field part, and we're just going to treat it as a ray, as an arrow that propagates through space. We just know the direction it's going, and that's all we really care about. Okay? The rays are straight lines that are perpendicular to the wavefronts. Right? So if we have these plane waves coming, then all the rays are perpendicular to that, and the next. Okay. So for these geometric rays, they move in straight lines. Right? So as long as you're moving through the same material, if you're going just in air, if you're going just in glass, if you're going just in any one medium, they just move in straight lines. They don't turn, they don't bend, they don't do anything funny. When a geometric array arrives at an interface between two surfaces, between two materials, then it can either reflect or it can refract. And likely it'll do a little bit of both. Right? And that means it will, they use the word bend, but I don't like to, and I will use that word, but don't think of it as the ray does this. Right? It's much, in the ray optic limit, it's much cleaner to think of it as it gets to that surface and it doesn't deviate, it's a straight line, and then it changes angle. Right? And then from that point on, as long as it's going just through the glass or just back out through the air, it's a straight line again. Okay. And the other thing you got to remember, got to remember, is the equations that we use are all for angles that are taken with respect to the normal. Right? Normal is just, physics speaks for perpendicular. Right? So we're going to take all of these angles of the ray. If we want to know what direction this thing's pointing, we're going to take the angle between the ray and the imaginary line that is perpendicular to that surface. Right? So this is a surface. I've kind of tried to draw it in 3D, and then this is what they usually show you in the textbook. Right? It's as if I came in with a razor blade and sliced through this block right here, right where this thing was hitting, right? And then you get this picture. All right, so then we have theta in is the angle of the input ray with respect to this imaginary normal line. The reflected ray will be, again, with respect to that same line on the other side now. And the transmitted ray will be going down this way, and it will also be with respect to that continued line. Okay? So here, all these angles are less than 90 degrees. Okay, so we'll start with reflections, because reflections are easy. I see my reflection in the bathroom mirror, and we call that specular reflection. That's where you can actually see an image of yourself, or you see an image of whatever it is you're looking at. So in this class, for the most part, we're just going to deal with the specular reflection. The angle in is equal to the angle out. Right? So as drawn in the previous slide, angle in is equal to angle out. Nothing more to be said. Okay? That one's easy. So we won't waste any more time on it. Refraction gets a little trickier. Okay, so refraction, by definition, is the change in the angle of the geometric ray as it transmits from one material to another material. All right, so here we're going to go from air to glass. We show the reflected ray for good measure, but we're interested now in this refracted ray, and the angle is no longer the same, right? Assuming that the index of refractions are not the same. And for air, the air has an index of refraction of 1. Glass has an index of refraction of 1.52 for typical glass, but it has a range. Right, it's around 1.5. All right, so the rule that is just given to you in the textbook, for the most part, and just said, okay, remember this. It's called the law of refraction, or it's called Snell's law, is n sine theta 1 is equal to n sine theta 2. So you take the index of refraction of the media that you started in, 1.0 say, times the sine of the angle taken with respect to the normal. Okay, so theta 1 is with respect to the normal, and then that tells you, right, if you, let's say you want to solve for theta 2. You just pull n2 over on this side, you divide, and then you get sine of theta 2 is equal to n2 over n1 times sine of theta 1. So that's how you do it. And we'll walk through an example of that. So this is basically what we were doing. We were going from air to water, and we were using Snell's law to calculate from this. We plug into there, we get this guy, do an arc sine, we're good, right? We're at the angle. Well, notice that there's nothing about Snell's law that tells you which direction that arrow has to go, right? I could easily write this as n water sine theta water is equal to n air sine theta air. I could move it to the other side, which implies that this geometry holds no matter which way the arrow is pointing. And so if I start with a laser underwater and I shine it up at exactly 22.1 degrees, the output will be exactly 30 degrees with respect to the normal. Right? So if it was a land-based laser and it hit this way, then it would be 22.1 degrees going into the water. If it's a water-based laser at exactly that same angle, it's just geometry, right? If you plug in one answer, you have to get the reverse answer back out. Okay, but this has some interesting consequences. Because what if I consider a larger angle? Right? Remember, as you go into the denser media, things veer towards the normal. Right? So this angle is always smaller than this angle when you go from light material to dense material. Okay, so we went from 30 and 22 to 60 and 40. That's great. And again, if I make it a water-based laser, angles just flip, but they're still the same numbers. So 40 degrees will get me 60 degrees. And if I keep going, if I take my water-based laser and keep moving it further and further and further out, notice that this angle is always larger than this angle. So at some angle, I'll get this situation, right? I will have not reached the surface yet, but this guy, because he's larger, has. Right? That angle is called the critical angle. When you get this scenario, that's the critical angle. It's very close to this. Right? I wrote in a number that would just barely have a little bit of transmission. Right? It's actually, the result is 89.99 something. I just rounded it up. But you're still getting some transmission. The light transmits out at this very, very skim angle. It just kind of skims the laser. If I had done it with a laser, you would actually see a laser beam that skims the surface, just above the surface. So now, what happens if I go even a little further and bring the light coming in from, say, 50 degrees, which is clearly larger than 48.75 degrees? Right? What happens? Well, it turns out that what you get is that, well, let's look at it mathematically. To get the angle in air, you take the arc sine of n water over n air times the sine of the angle that it came in with. So if we plug in those numbers, sine of 50 degrees is 0.766. And we take 1.33 times that, because that's what n water over n air is, we get 1.02. And the arc sine of 1.02 is not a real number, right? Because sine can only go from -1 to +1. So this has no real solution. So if the math is telling us that there's no real solution for the angle of light that is transmitted out of the water, then the math is telling us that the light doesn't get transmitted out of the water. And that's exactly what happens. If you come in at a large enough angle, there is no real angle that satisfies this Snell's law, and so there is actually no light that transmits into the air. It's totally reflected. And that phenomenon is called total internal reflection. And again, the critical angle is just that ratio, the inverse sine of the ratio of the indices. When you go from high index to low index, when you're trying to do this. If you're going from like air to water, there's no angle where you get total internal reflection because every angle has a sign that will work. Right? But going dense to light, you get an angle where the light is completely reflected. And you guys have seen this when you look, if you ever go and peek, I ran out of time, I was going to go look for some pictures. But if you get into a pool and you look out at a very shallow angle, it'll look like a silver mirror. Right? If you go to the side of a fish tank, I'll try and provide some pictures in the online. But you guys can look it up. If you look at a fish tank at a very shallow angle, you'll also know it looks very silvery. Okay, so there's a big section on prisms. So let's walk through working on prisms, right? There's really not that much to it, but it seems like what it really is, it's an exercise in applied geometry. And if you think about it, a prism, it's just a slab of glass, right? We've already done this problem. All it is, everything is linear, right? You don't have to worry about the whole system at once. Don't worry about the fact that there's another surface here and there's all weird stuff going on. It's just light hitting a tilted surface, right? We know how to do this. It's Snell's law. That's all there is to it, right? Later on, I'm going to deal with this, but let's deal with one thing at a time. So I have light coming in to a prism that is a 60-60-60 degree prism, an isosceles triangle. I'll tell you that the index of the refraction of the prism is 1.50. What happens to this light? Right, let's see what happens to that light when it comes in. Okay. So we know we're going to draw, at this interface, a normal. Right? And we know that when it comes in, it is going to, so I promise I won't take pictures of you doing this. Everybody tilt your head, right? If you tilt your head, you'll see that this is just the slide that we've shown many times, right? And the angle in is with respect to this normal, right? Because this is the surface of interest, surface A. So we look at the perpendicular to that surface and we say this is the angle we're interested in. That's theta in, or theta 1, and this would be theta 2. Right? And we know that when the truck hits molasses, it's going to bend towards the normal. And so it's going to bend downward a little bit. And then it's going to, at some point, I don't know where, but at some point it's going to hit this other surface. And then there we will, once we've dealt with this one, then we'll come and tilt our head the other way, and we'll deal with that one. Okay? Okay, so we now know theta 1, theta 2, and I'll just take the opportunity to label theta 3 and theta 4 with respect to this normal. Right? Okay. Now we have to figure out what those angles are. Right? So here's where it's applied geometry. I'm going to go ahead and label a whole bunch of other angles just so we can unambiguously talk about them. Right? These labels have no meaning. I could have given them names like Charlie. Right? I'm just going to make them easy and say theta A, theta B, theta alpha, beta, and this one would be gamma, but we don't actually care about it. Okay, so let's see what the next thing we can think about is. So if you remember from some geometry that you guys have done, you may remember these kind of diagrams where they have these kind of Z-shaped things. And from here, you can say a lot about similar angles, right? So if this angle is 60 degrees, it turns out that the inside of the Z are similar angles, right? If you have two parallel lines here. This is a parallel line, this is a parallel line. Any line that intersects them, this angle will be equal to that angle. Right. And since it's not a geometry class, I won't go through a full derivation of that. Hopefully you guys kind of remember it, and hopefully you guys can kind of see that if I start squishing and stretching the Z, you see how the angles change together. Okay? So that tells us something. This angle is 60 degrees. Right, because it's similar to this angle. Okay, well, if we figured that out, then we can say, well, come on, I'm not interested in theta A, I'm interested in theta 1. Right? Incoming ray is at 0 degrees. We will deal with the case where it's not. Okay, so if that's 60 degrees, then if we look here, by definition, the normal to the surface that we've drawn is normal to the surface, is 90 degrees, right? It's perpendicular. So this full angle is 90, which means theta 1 plus theta A has to equal to 90, so theta 1 is just 90 minus theta A. So if this is 60, that's 30, because that makes a 90-degree triangle, 90-degree angle right there. All right, we're making progress because we now have one of the angles that we can plug into Snell's law, right? And you all have calculators, so you could do this, right? 1.0, 1.5, sine of theta 1. It turns out, I think, to be 0.5. And then you take the arc sine of it. And then we get an angle theta 2. So now it gets tricky. So we'll slow down. I have theta 2 here. The next thing I want to know, right, if I want to propagate the system through this light ray through the system, clearly it's going to get to here, and I'm going to either need to know theta 3 or theta 4 to do Snell's law. right? But I don't have theta 3, I have theta 2. So what can I do? Okay. 2 steps to get to theta 3. 3 steps, maybe. We can figure out what theta b is because, again, this is 90 degrees. Right? Since that's 90 degrees, I can now subtract 19.47 from 90 degrees and get that theta b is 70.53. We now have 70.53. So let's see if we can figure something else out. And here is the next geometry trick. That's a triangle. What do we know about triangles? 180 degrees. They sum up to 180 degrees. Okay, so if that has to sum to 180 degrees, and I've just figured out what this one is, and I started by knowing what that one is, then it's pretty straightforward to figure out, okay, so theta b was 90 minus 19.47, and theta c is equal to 180 minus theta b minus theta a. We're almost there, right? Because now, from the fact that this sums up to 180, I've gotten this angle, and that angle is a complement to this one. These two obviously sum up to 90 degrees for the same logic that we had on this side, right? This is by definition the normal, so it's 90 degrees to the surface. So once we have theta c, theta 3 becomes very easy. It's just 90 minus theta c, which gives us about 40.5 degrees. We have theta 3. We want theta 4. We have Snell's law, so we just apply it, right? Being careful, of course, that theta in and theta out here was air to glass, and on this side, it's reversed. It's from glass to air. So one thing you might have to check is, will this actually even work, right? Because we just found out a moment ago that if this angle is too big, going from glass to air, it may actually just reflect. And there are some prisms that are designed that way. There are some prisms that are designed to be used so that the second surface is purely reflecting and then it comes out the other side, right? But if we plug in the math and it turns out that this number is less than 1, then we get a real solution. And whatever that angle turns out to be, in this case 77.1 degrees, it's okay.